So welcome to Material Science lecture. So this is Module 1, Lesson 3 on the atomic bonding of materials. So in this lesson, the outcomes for this lesson, so we have three lesson outcomes. So by the end of this course, you should be able to recall the ionic bonding is an attraction between positive and negative ions. So you should understand that covalent bonds involve the sharing of pairs of electrons. And also you should be able to describe metallic bonding and its strength in terms of ions and delocalized electrons. Just a little bit of the introduction. For ionic atomic bonding, you should already have learned this in your previous study. Ionic bonding is a chemical bonding process that is responsible for the interaction between atoms and molecules. So there are three basic ways that the atoms can form bonds. So they are electron valence, the outermost electron can be transferred from one atom to the other, or they can share the electron valence between the neighboring atoms, or the outermost electron can delocalize from their energy level and then the outermost energy level and share with all the atoms in the materials. So there are the three basic ways the atoms can form a bond. So before we go any further, I would like to talk about how do atoms bond. So atoms, they bond when there is any space in their outer electron shell for more electron. So when there's a space, when they are not complete, the outermost electrons not complete, they're not stable. So they want to be stable, so they will start forming a bond. So they either will donate, they will lose, or they will share the atoms between them. But whatever it is to make the outermost shell full, so they want to be stable. So noble gases with their full outer shell do not easily form bond. So noble gases such as neon here, because of their full outermost shell, they cannot be bonded with other things. So helium, neon, argon, krypton, xenon, and radon are all noble gases. So they all have full outermost shell, so then cannot be easily bond with other things. But neon atoms, if you look at the neon light, so you might be wondering if they're not interacting with each other, how do we have that neon lights? So neon atoms are attracted to each other by London dispersion forces. I'm not going to talk about it. So this is just a fun fact. You can Google it and try to understand it by yourself. So in an atom, the inner complete electron shell, so we have a few electron shell, but we have one with the outermost which is not complete, and then we have the one inside that is complete. So this inner shell were held tightly by the positively charged proton in the nucleus. However, this inner electron shell will shield some of this nuclear charge from the outermost electron. And the outermost electron can only feel the excess charge of this nuclear charge. So for example, here I have chlorine. So chlorine has 10 electron in the complete inner shell. So they have if you look at the shell number 1 and 2, so this is complete, but shell number 3, it only have 1, 2, 3, 4, 5, 6, and 7 electrons. So it's not complete. So this inner electron, the negatively charged electron, will shield the nuclear power from the proton from these outermost electrons. So what will happen? This outermost electron can only feel the net charge, the effective nuclear charge of the positive 7. And Same with sodium. So sodium with 11 proton and 11 electron. And it has also 10 inner electron, leaving only one effective nuclear charge to hold the outer electron into its position. So this is why we see non-metal with nearly full electron hold to their electron stronger than the metallic element with nearly empty shell. So in this case, with the sodium and chlorine, so what will happen? Chlorine will will accept one charge from the sodium, because sodium can only, the outer electron can only fill one effective nuclear charge, so it's quite weak. So what will happen? It will try to donate that one electron, because it cannot held it there. It's not strong enough to hold it there, so chlorine will happily accept it to make itself stable. So they both is going to be stable when they donate or when they accept it. So that is how atoms were born. It is because they want to become more stable. So we know atoms love to be stable. And the way they can achieve that is by having a complete number of electron valence. So this is electron in the outermost level. So this is to achieve stability. So this valence will allow atoms to have different properties. So many elements are not chemically stable by themselves. So by sharing electron or donating, an atom can gain stability. So octet rules state that atom gains or lose electron to attain an outer shell electron configuration as near as possible to the noble gas. So since noble gas, we said that noble gas is stable. So this is why atoms wants to gain or lose or sharing their electron. It's because they want to get to this configuration. And there are three different primary interatomic bonding. So there's one which is ionic bonding, covalent bonding, and we have metallic bonding. So now I would like you to pause this video, take a piece of paper, write down what you can remember of all these three interatomic bonding. And when you are done, get back to this video and see if what you remember is correct. So let's begin with an explanation of ionic bonding. So ionic bonding occurs between metals and non-metals. Ionic bonding involves transferring of electron from one atom to another. So the easiest example I can give you is the sodium chloride. So sodium chloride is our table salt. So this is the sodium chloride configuration. So we can see sodium has one valence electron and chlorine has 7 electrons. So if we transfer that 1 electron from sodium to chlorine, then we get this electron configuration, which is going to be stable. So the electron configuration now is the configuration of the noble gases. So what we get is the sodium ion and also the chlorine ion. So sodium ion, since it's lost its electron, it's going to be positive. So we call that cation, and it has positive charge. And the chlorine is going to be negative, and we call this as an ion. So an ion has a negative charge. So an ionic bond is going to be between ions. So it is a connection between cation and anion. So cation is going to be positive, and since they lost their electron, and anion is going to be negative. So since they gain an electron. So they will form an ionic solid. So how well is this ionic solid is going to held together is basically based on Coulomb's law. So remember Coulomb's law, if we have a larger charge, it's going to be a larger attraction between the two atoms. And also the greater the distance between the ion, so if the radius of the ions is bigger, means the distance between them is bigger, so it is going to be less the force. So if we have a really small ions and a large charge, we're gonna have a stronger interaction. Here is our sodium chloride again. So here is our sodium, the purple color, and there's gonna be a positive charge with that sodium ion. So, and they're going to organize themselves in this like a perfect organized structure. So the purple one here is the sodium. So this really have a high melting point and high boiling point. So this is how they're going to pack themselves together. So to break this apart, the easiest way if we use water. But this sodium chloride is very, very stable. But how stable they are, we are going to look at this with Coulomb's law. So what determines the stability of how well this atom held together? So it's simply Coulomb's law. So from Coulomb's law here, we can see if we have the same charge, so if we have the same charge, what we can see is there's going to be a repulsion. And if we have the opposite charge, there's going to be attraction. And if we look at the formula, we can also see that the bigger the distance between the atoms, the less the attraction would be. So R here is the radius of the atoms. So let's throw that sodium chloride up here again. So sodium chloride, so sodium, which is going to be the cation, and the chlorine is going to be the anion. And then there's something that we call as the lattice energy. So lattice energy is just the way we measure how well the lattice or the atoms pack together, held together. So that is the lattice energy. So what do you think if I'm going to move up from sodium chloride to sodium fluoride? So pause this video and have a think. So if you look at this diagram, so this is sodium fluoride. So here the purple color is still the sodium. So what you can see, the fluoride, so fluorine is having a smaller radius if we compare to chlorine. So what will happen is the distance between them is going to be reduced. So the smaller the distance, going to be the greater the charge, the greater the force. So the lattice energy is now going to increase because those ion is closer together. So that is how the Coulomb's law, that is how you can use the Coulomb's law to justify the stability of this ionic bond, the ionic solid. So now what will happen if we move from fluorine to bromine? So what we will have is a sodium bromide. So again, you can see the sodium ion here is going to be the same size, but the bromine is having a bigger radius. So you can see with the atomic number, from there you know that the radius of that atom is going to be bigger. So the distance between them is going to be bigger as well. So the lattice energy is not now going to reduce. And the same is going to happen when we change from bromine to iodine. So we have sodium iodide. So the bigger the atom radius, it's going to reduce that lattice energy again. All right. So as it gets bigger, the distance between the two, just due to Coulomb's law, we can see the decrease in the energy between them. But what are the other things that can affect the stability of this ionic solid? So if we look at the Coulomb's law again, we can see that the other things that can affect it is the charge. So if we run the sodium chloride again and we run it versus the barium oxide. So the barium oxide is going to have totally different charge, as you can see here, and there's a greater difference between those lattice energy. So in other words, as we increase the charges, we increase the ionic bond between the two. So now I hope that you can connect the microscopic structure to the macroscopic properties of the materials. So using Coulomb's law, we know the greater the charge and the smaller the distance between the ions, the greater the bond strength is going to be formed. So the more stable the structure that is going to be formed. So now let's move on to covalent bonding. So I use this image of plastic or polymers because covalent bonding always involved in the bonding of the polymer molecules. So covalent bonding happens when non-metals element react with another non-metal elements. So it involves the sharing of electron instead of transferring electrons. So what will happen is electron will be shared between two atoms. So two or more atoms. So the sharing of the electron will allow the atoms to attain the equivalent of the full outer shell. So now again, they want to be stable. So by sharing the atoms between them, they can attain that stable electronic configuration. So polymer molecules contain a very large number of atoms linked together with covalent bonding. All right, so now I would like to use water molecules to explain about covalent bonding, so the sharings of the atoms to you. All right, so this is an example. So we have water molecule consists of two hydrogen atoms with one oxygen atoms bond together using bicovalent bonding. So hydrogen atoms has one electron in its outer shell. So to be stable, it needs another one. And it can only form one more bond. And we look at oxygen. So oxygen has 6 electrons at its outer shell. So it needs 2 atoms to become stable. So by sharing electrons with 2 hydrogen atoms, each of the hydrogen atoms sharing 1 electron, it can attain octet. So remember octet group, it needs to have a full outer shell, a complete outer shell. So by sharing with 2 hydrogen, it will develop these water molecules with covalent bonding. So the covalent bonding will happen with by sharing the outermost electron of the hydrogen and also the oxygen, 2 hydrogen with 1 oxygen. Another example is methane. So methane consists of 1 carbon atoms with 4 hydrogens. So one carbon atom has an atomic number of 6. So we know it has a valence electron of 4. So it needs another 4 to attain octet, to be stable. So what it needs it needs to bond with 4 hydrogen bonds. So 4 hydrogen, each hydrogen have 1 electron in its outer shell. So what it will do, it will, by sharing 4 electrons with 4 hydrogen atoms, each sharing 1 electron, it will attain octet. So the bonding between these 4 hydrogen atoms with the 1 carbon atoms is what we call as covalent bonding. So by sharing these 4 atoms of hydrogen with 1 carbon, it will create a compound or a molecule that we call as methane. And then we have the metallic bonding. So this is the most important for this course of material science. So metallic bonding is how atoms of metals is bonded together. So in, I think, almost 80% of the topics that we're going to learn in this subject is involving metals. So metals are going to be bonded together by metallic bonding. So when we talk about metallic bonding, it is important that you understand that you cannot have one metallic bonding. You have to have a number of atoms sharing the electrons together. So for example, when we talk about ionic bonding, so we can form one ionic bonding between one sodium atoms, sodium ions with chlorine ion, so you can form one ionic bonds, and the same with covalent bonding. However, with metallic bondings you can't do that, so let me explain. All right, so I have these aluminum atoms here. So these aluminum atoms has these 3 electron valence outside in the outermost shell. So they're weakly bound to the nucleus because of the shielding effect of the complete inner electron shell. So what will happen is they will delocalize themselves. So they will detach themselves from these atoms. So when we have a cluster of aluminum atoms, what will happen is this metal atoms, the aluminum atoms that are grouped together in a block of metal, and the outer electrons of all of these atoms will leave the individual atoms and become part of the common electron sea. So all of these electrons are shared by all of these atoms. So these electrons are shared by all of them in this block. So it creates a sea of electrons. So, and the proton is kind of held together in this sea of electrons. So that's the basic concept of the metallic bonding. So in summary, metallic bonding is the electrostatic attraction between the positively charged nucleus of the metal and the delocalized electron in the metal. So the valence electrons are mobile and can conduct heat and electricity easily. So the delocalized nature of the bond makes it possible for the atoms to slide past each other when the metal is deformed. So it makes them ductile. So I've told this in the first lesson. Because of the delocalized nature of the bond, so the atoms can slide past each other. So the metal can be easily formed. So that's why metal can be easily shaped into different shape. So now that we have learned about the atomic structure, which is from the previous lesson, and we've learned about interatomic bonding, which is this lesson, I want you to think, take a piece of paper, ask yourself, answer this question: why do you think it's important to study the interatomic bonding and the atomic structure? You don't have to answer, you don't have to give me the answer, just ask yourself and see if you can see the importance of studying these 2 lessons that we have learned so far. So in summary, in this lesson, we have learned that ionic bond involve an exchange of electron, and the atoms are held together by electrostatic force between the oppositely charged ion. And then covalent bonding involves a sharing of electrons so that the orbitals of the outermost energy level in the atoms are filled. And then we learned that metallic bonding is the electrostatic attraction between the positively charged nucleus and the delocalized electron in the metals. All right, so that's about it for the first week of lecture. I hope now you can answer all the questions in the tutorial, and we'll discuss that in class. All right, thank you very much.